Hey guys, we're back now, and this is going to be the wiring video. Have you ever put a video together and you try to think of every possible thing, and then after you get it uploaded, then what do you think? There you go, you forgot some things, some points. So I'm going to try to cover some points in this video before we start showing the wiring diagrams that I should have covered in the previous video, and also to answer some comments. I figured I'll just do it in this video also. And while I'm here, let me just take the time now to just thank every one of you guys out there, for your support, your comments, your interests. And, we're all here to learn. I'm no expert in everything, and I've been in electrical for 45 years. And do I know it all? No, absolutely not. Am I even considered an expert? Absolutely not, because there's always something new to learn. So let me start off with saying I want to give maybe some special thanks for the guys that's been following this video series. Now, this is not to short any of the other people out there, that's not, maybe hadn't commented, and, they'll watch a video, no comments, so this is for everybody. But for some of you guys out there, I'm going to start off with Dave. His channel is Spelunkered, and I wrote this stuff down because I want to cover these points. I don't want to miss them, because this is the third time I'm editing this video, and I've rendered it twice, so now I'm going to do it again. So hopefully this is going to be it, okay? So Dave for Spelunker, he had a question out there, and he wanted to know he had a couple of questions about the starter motor circuit, about the two solenoid windings, what's the little dancing routine that goes on when these things get energized, and also, why is the current, it goes up so high, and then as the motor armature turns, then the current drops down. So Dave, for you, I've got that saved for you at the very end of this video, right after the wiring diagram. So I think it's good too, we'll cover it in the video, even though we had an ignition switch fade, burnt some wires up, the starter motor, solenoids, it's all part of the same circuit. So let's, we'll put it all right there together, and we can go over that. Okay, and also, I'm going to put a link in here for these guys in the description in the bottom of this video. So, by the way, Dave, he's a guy, he works on anything. Makes things, he got a bracket to make whatever he needs. So, I seen he's got a welder, he works on a Dodge, he's got a Volkswagen, so he's a do-it-yourself guy, so you can learn a lot of stuff from him. Great guy to talk to also. Okay, we got another guy, Steve Robb. Now Steve, he's been very helpful. He's thrown out a lot of comments and good ideas, and also he'll correct me. For example, in the last video where I mentioned about the RTV sealant, I posted a comment to Steve, and I said, that interview that I had with my friend Walt, the chemical engineer, that was not rehearsed at all. I mean, we just winged it, and I was just throwing stuff off the top of my head. And when he mentioned about sealing it up for the environment, just right off the top of my head, I'm thinking RTV. And then later, after this thing gets posted up, I'm thinking, oh my. Now, why did I even say that? So you're right, Steve, about putting RTV in there is not a good thing because of ammonia, that it can create, and that is corrosive to, the copper. So good catch on that. Okay, we got another fella here, Don Joe. He's been following along on this channel for quite a while here, along with the others that I mentioned. Got some good comments. Always looks like that he wants to be kind of scientific, wants to get down into it, wants to see what actually happened, and hopefully in the previous video, hopefully we cover some of that too. So I appreciate all your comments, Don, and good feedback on everything that you give. Okay, and also, Don, you left a good comment about the ignition switch, about inside the contacts. But there's another thing that I thought about later. Of course, if you have the dissipation of the heat right there with the terminal that we talked about, and it's going down the wire, well, of course, naturally, it's going right back into the contact switch for the ignition switch. And that would be great to open it up and look at it. But I tell you what I even thought would even be better is, some of these relays, like this fuel pump relay, it's, we got 6 pins on it there, and, open this thing up, looking inside, maybe a little electronics. Another thing I saw was a starter lockout relay. You remember on the diagram, it showed a little box inside of another box. Okay, you could take that to be electronics, the box being inside. Well, looking at the relay, it looks just like a standard relay. That might be a good thing to look at, and maybe make a little video on this whole thing right there. But, man, I have got so much stuff going on right now. The Buick has thrown up another check engine light, not for what I worked on. Now I got a P0741 torque converter clutch stuck off. I need to work on my truck really bad, so here I need to do a timing belt change on that. I need to do plugs, I need to do wires. My power steering fluid is leaking. I have an engine oil leaking. Let's see, my radio stopped working. This is all on the truck. What else is going on?
Air conditioning?
The air conditioner doesn't work now. Let's see, what else? Oh, if I press the emergency brake down, I don't get the red light coming on anymore. And there was one, oh, and if I leave the ignition switch and I open the door, I think I used to get a chime. Now I don't get a chime at all now, so take your pick, which one of those you want to work on. See, so we got so many things, and that would be a good thing for the video and the switch, and we'll get all caught up here, you know, that'd be a great video to put that together. So anyway, I want to hold off on that. Okay, then we got another fella here. His name is Jahan, okay. He's from Saudi Arabia. His channel is called The Learning Zone. Now this guy, I've watched his videos. This guy just works on everything. TV remote control just broke. He'll take troubleshoot that. That was a good video, John. You did a good job on that. It shows how to do the repair. He's worked on vacuum cleaners, window air conditioners. He's worked on automobiles. I think whatever breaks down, he's working on it. So he seems to be a great guy to talk to, and you can learn a lot from him also. So be sure to check him out. Okay, we got another fellow here, DJ Devon 3. You know, DJ, I don't even know what your first name is there. So I'm just say DJ. I've always, when I responded to you, I always called you DJ. So I'm going to call you DJ. Now, here's a fellow you can learn a lot from. He has an automotive channel. He's over there. He's got a Mazda 626. He is restoring. I believe it was for your niece, I think. And so he's got a video series, just step by step, going all the way through. Great teacher, step by step, to show you all how to work on the Mazdas. He also has a few videos on, I think, Ford Probe, and he also got some on Ford Tempest. So be sure to check him out also. Okay, the last one I got here is Thomas, EXOVCDS. Now this guy works on Volkswagens, BMWs, Audis every day for a living. And it's always a pleasure for me to go over there to his channel and watch him work. I mean, this man is a machine working on a machine. There's no lie. I mean, all his moves are just methodical, step by step. You see them in real time. You can see there's very little editing as far as him doing the actual repair. He's got a lot of good diagnosis over there. You can learn a lot of stuff from Thomas. Also, Thomas, I've talked to him, you know, offline, you know, privately, and he's a great guy. And you know, just through the little bit of conversation we had, I can tell he's a great guy to talk to. Okay, Thomas, one more thing. I hope you don't mind, but if I get these comments, you know, about Volkswagens, and it's not pertaining to the video I'm working on. And you know, there's questions about turbos, and it's like, well, yeah. So I'll give my feeble answer to it, but then I'll recommend your channel and I'll tell them where to go to. So I hope you don't mind that, and I'm sending them over to you. You know a lot more about these cars as far as the VWs and all than I do. So hope you don't mind that, and hopefully you can pick up some subscriptions, you know, from the guys coming over there to check out your channel. And I think that's going to wrap it up. So let's get ready and let's get started on these wiring diagrams. And one more thing to keep in mind, I tried to cover everything I could think of, but you know what? I'm sure there's going to be something I'm going to forget. Okay, let's get started on the wiring diagrams. All right, now these three drawings right here is for the engine performance. Okay, now these are the original circuits. They're intact. I haven't doctored them up or done anything to them. I'm just going to set them there just in case if we have to refer back to them. Same thing holds true for here. These are the original, haven't been doctored up. These are the power distribution wiring diagrams, also three of them. So we're going to set those aside. And what we're going to look at is the ones that I actually worked with, okay? This is the power distribution wiring diagrams, okay? And you can see I kind of color coded things up a little bit, try to make things a little bit easier. Okay, now problem started all right here, let's say at the ignition switch. So let's take a look and let's focus on the ignition switch. Now, the ignition switch is on power distribution wiring diagram number 2. So, if you look right here, as you remember, I told you that a box that goes around a component is showing us all the internals inside of that component, in this case the ignition switch. Alright, well, let's see. You see right here where we have a red wire coming down, that's our B plus coming in on terminal 30. We also have a 30 over here coming in on this here other 30. Alright, now let me hold you right there for a second, because you can see right now I've done a little doctoring right in here. You notice I have an open connection in here. Okay, there is no connection between here and here as it shows on the diagram. Let me show you that right now. Okay, here's the diagram. This is the original. As you can see, 30 is tied to 30 all the way across, right? Okay, so we know that this is not together internally inside the ignition switch. The reason I know that is because I actually done that with the continuity check in the little chart that I showed you just earlier. Okay, so the new switch actually shows this as being open. So I thought, well, maybe there's a problem in the wiring diagram when Mitchell redrew them, and maybe the OEM prints from Volkswagen shows this connection open. All right, let's take a look at that. Now, here is the Volkswagen diagrams. Here's our 30, here's our other 30. Take a look inside the switch. You see how it's all tied together? So there is no problem as far as in the wiring diagrams that Mitchell did. They did a good job. They only copied what VW had done. Okay? As you also may notice, I went ahead and put in here, the size of the wire on both of these over here. Okay, in fact I did that for each one of them. I made a notation of which wires were burnt. This one actually here, the black wire, being laid up there against the other 2 wires that were actually burnt, you might say, with the insulation. This one had just barely started melting the insulation, but it got down to the strands, but I'm not quite sure if it actually was touching. Okay, over here, this wire, of course, the red with the gray tracer, that was burnt. And of course this one up here, this wire was burnt with this wire, and this black wire, maybe the black wire. Okay, now if you notice up here, I got 30, it says on the bottom of the switch. Here, 30 is on the top of the switch. Alright, let's just make sure we're on target to know where these 2 are at on the switch. Alright, the 30 on the top that I'm referring to is that when the switch is in this orientation, there's my small posts at the bottom. They're in a horizontal plane. My 30 on top is here. My 30 on the bottom is here. Okay? And then, as I mentioned in a previous video, this dash line is showing the 3 wires that had an issue. Okay? Alright. Alright. Now this, a lot of this stuff that I'm going to show you, let's look at it as just learning to read diagrams. Maybe a lot of it may not be pertinent to what we want to do here. Ignition switch failed, burnt some wires, corrosion. Well, let's get some practice reading some diagrams. Alright, we have this B plus wire coming in. This is a positive 12 volts, and it says A, right? And it says that, in fact, B is the same, saying that this is going to come from diagram 1 of 3. Alright, so let's go over and let's look at those 2. First, we'll look at A. A is right here. So now, you can see, if we follow up, we follow up, we follow up, and here we have a 110 amp fuse. Remember the fuse that I showed you right there behind the battery? We go over, we come down, and we're back to the battery. 12 volts positive. Alright, well, let's follow it on down some more. We come down, and we can see that we're coming to E. Alright, Now, we just kind of right now what we're doing is we're looking to see how these circuits are protected, what kind of fuses. You know, I mentioned too about it looked like, say, these fuses, these circuits are not protected. Well, they're not, but in a way they are. And I think I'll try to explain that. But let's follow E out, and it says go to diagram 3. All right, so we go to diagram 3. We find our E, and you can see right here, this is where E is coming in, and notice that it's feeding this bus. And this bus is connected to all these fuses here, all the way across, protecting all these individual components and loads out there, okay? All right, so that looks okay. Well, let's take a look and follow D. C. No, D. D. D is the yellow. Says it's going to 3 also. So let's go back over here. We find the yellow, which is D. And again, we're feeding a bus. And there's all our fuses connected to it, feeding all these different loads out here. Okay? So far, so good. Now, if we look right here, we see there's a splice, and we can see that we're taking off, we're going through another fuse, protecting these components, okay? Now, let's follow A, and let's look at that a little bit more. So we know it came down through a 110 amp fuse, okay? Now it's coming down through A, right? Now we're connecting back over to A, right? Here's our A. Now this is going to go through the 30 that's on the bottom of the switch. Remember, there's a break internally in the switch. So this here is going to be feeding in the on position this here C. All right, now this C is telling us it's coming from the 13-fold auxiliary relay. So we want to look at diagram 1. All right, so let's go back to 1. Let's find our C. Our C is right here. Okay. So now let's start looking at this. If I go down here where the splice is at, I can see there's a fuse feeding the light switch. But I don't see nothing over here. Okay. And if I go up to here, and I come up, and I come over, then you can see it's feeding the dual horn relay. And it's also feeding one side of the coil for the load reduction relay. Now, if you look right there, it does say, well, what's going on here? I don't see a fuse. 110 amp fuse, right? This is what's feeding this. Well, let's take a look at the dual horn relay, because maybe you're not necessarily seeing every single thing on the power distribution prints. Power distribution is only going to show you the positive side of the circuit and where the component's connected to. Now you'll see some of the fuses, but it's not necessarily that you'll see all of them. So let's take a look at this dual horn relay circuit. All right, as you see right here, we're on the horn circuit now. Now take a look right here. Here's our ignition switch. We're in the on position. Terminal 75. They didn't put that there, but that's where I put it, which is right here. This is where we started from, coming through the switch. Okay. And just as a reminder, you can see that we're coming in on terminal 5 of this S1 connector. This is the 13-fold auxiliary relay panel. So let's see if we can find this wire right here. So we look. There's our black with our red wire. Okay, we have a splice. Now take a notice of this. You see this line? You see how it's dashed? And this line over here is solid. Alright, this dashed line means that we're not seeing all of the wires that's coming into this point, into this splice. Okay, well, you want to see where they're at? Come back over here. You see there's our black with a red wire. There's our splice. And here's all our other wires, okay, that we do not see over here. That's what the dashed lines means. Okay, we're coming down. There's our S1 connector. There's our 5. Okay, So there he is right there. We're coming up, we're going over, we're going to our dual horn relay. We're on terminal number 4. Let's follow back over here. Here's our dual horn relay right here. There's our terminal 4. Now, do you see any fuses in there, in any of this circuit that we just looked at? Mm-hmm. The only one that I saw was 110 amp. All right. So, well, you're thinking maybe, well, how can we get away with this gauge wire is maybe 14, 12 gauge wire, and yet this thing is protected by a 110 amp circuit, or fuse, right? Now, I actually looked to see if I could find anything with DIN standard about the control wiring and branch circuits, feeder circuits, you know, taps and things of that sort. This would be like a tap. Now, since I'm a licensed electrical contractor, and I'm going to just put my own thoughts in this, right? Let's get the code book out. Okay. We have the NEC code. This is 2011. They just came out with 2014, but the ampacities of the wires is the same, hasn't changed. But let's kind of look at it a little bit. All right, I'm looking at an insulated conductor, copper, not more than 3 current carrying conductors in a raceway cable or earth, and it's all these here wires are based on an ambient temperature of 30 degrees C. All right. Now, if you look up here, you'll see there's a column, 60 degrees C, 75 degrees C, 90 degrees C, and you can see it just keeps on over, right? This over here is for the aluminum or copper clad conductors. These 3 columns right here is for the copper. And you can look right down here, and you can see where our ampacities are at for copper, which is what we're going to be looking at. All right. Now, let's look. Let's just... I looked at the DIN standard for a 2.5 millimeter squared area of wire, and it went directly to 12 gauge. Now, what I measured, I went out there with a dial calipers. I measured it, and it's actually closer to 14 gauge. Actually, there is not a direct conversion from metric straight over to AWG that we use in the USA. It's actually like a 13 gauge. It's like between a 12 gauge and a 14 gauge. So let's look at it as a 12 gauge wire. So I come down, I find 12, right? Now, all of these here temperatures right here is based on the insulation that's on the wire. Well, let's look at it. It's got a 90 degrees C insulation. And by the way, what do you protect the wire for? It's basically they'll run a current through a wire. How much current can we push through this wire before this insulation will start to melt? That's what the ampacities are based on. It's based on the insulation. Because if you look, you say 12 gauge. Now, remember I told you 12 gauge is good for 20 amps. That's for the overcurrent protection, the device, the fuse, circuit breaker. But if you look right here, if the wire with the insulation of type TW, that's a thermoplastic wire. W means it can be used in a wet location. Has a 60 degrees C rating. But look, I slide over. Now that same wire, remember the wire has gauge, or the copper has not changed in diameter. We've only changed the insulation type. Now it's good for 25 amps. Now if I come over here to 90 degrees C, now that wire is good for 30 amps. Okay, getting back to the tap rule. The code here says that if you're going to tap onto a wire that's larger, and you're not going to, ideally, if you got a wire and you got it protected with a circuit breaker, let's say 110 amps, and you take another wire and you're going to tap in there, right onto that wire, say with a bus bar or something of that sort, ideally, it'd be good to put a overcurrent protected device right there at where the source of that wire is, the smaller wire. Well, sometimes it's impractical. So they come up with a tap rule saying that if this here smaller wire meets 1/3 the ampacity of the larger wire, it's not over 10 feet long, It's mechanically protected. In other words, it's not going to get damaged in any way. And probably being up under the dash, it don't look like it's going to get damaged or anything like that, you know, as far as abrasion or anything like that. Then you can use a smaller wire, as long as you don't go past 10 feet, 1/3 ampacity, mechanically protected, and you're good to go. And you don't have to have a fuse there. So you can run that wire out 10 foot and you're good to go. Now, like I said, I don't know what the automotive code is because I can't find anything on it. But I'm sure they probably have something of that sort, you know, with, you know, a tap rule. So that's what I'm going to base that on. Now, do I know that for 100%? No. But that's probably what I think is, you know, going on. We can also, let's take a look at another one here maybe. You saw the same thing here with the load reduction relay. You see it's coming up, it's feeding one side of the coil. Well, if you come right over here, you can see right there, feeds the load reduction relay. Again, you don't see any kind of fuse or anything in there. So again, I'm thinking they're using the same thing here. They're using a tap rule on that, okay? All right, let's look at B here a little bit. Now you see that B, which is also 30, but it's on the top of the switch. Now you can see that in the on or start position, then off we go. Got a splice and it's feeding this here, right? This fuse, this one fuse for this here circuit, for the instrument cluster. We also feed an airbag control module. Now I've already looked at this, there is no, and I went to the airbag control module directly to see if there was any kind of protection in there before it gets to this. There is not. So let's see, just back up, okay? So let's just back up and let's see if B goes to the same spot. So I'm going back over to B, I'm looking over here, and again, you see, it's the same point as A, which means it's coming right back through that 110 amp fuse again. Okay. All right. So the same thing over here. I couldn't actually find this switch, but my guess is it's probably the same thing. All right. Now we're also feeding this here fuel pump relay. All right. And we also, if we come over to this one right here, and if we're in the start position, right, we're coming down with our 12 volts, right. We're going to go over to the fuel pump relay, and again you can see that this is only going to be 12 volts there while we're in the start position to the fuel pump relay. And we'll come back and look at him, see what kind of protection he's got, because right now on this diagram we really don't see nothing, right? So we'll come back and take a look. All right, we have the starter interlock relay. So here, you know, if you remember, we were coming out of the start position on the ignition switch. We head down here to the starter interlock relay. All right, so if we go over here to the starter interlock relay, look right here, there's our 50B coming out of the ignition switch in the start position. We slide over here to the starting circuit. There's our 50B. All right, so we're coming down, go through the switch, comes out, and down we go. So this is as detailed as we can get. Again, you do not see any kind of protection in there. We come right on around, don't see no protection in there. And of course, we don't see no protection going out to the starter. Again, I'm gonna look at that as a tap rule. So again, we don't see any kind of overcurrent protection in there. Okay. Now let's get back over to the fuel pump. Now for the fuel pump, we're going to look at that on the engine performance circuits. Okay, we were talking about this here fuel pump relay. Now you notice that there is two positive 12 volt lines coming in here. Okay. Now remember, this is not showing us all the connections for the fuel pump relay. This is the power distribution print. That's only going to show us the positive 12 volts that's going to each component. So let's take a look over here at the fuel pump relay. Now right now we see that it's still being fed through that 110 amp circuit, and we want to find this fuel pump relay. So let's get over here on the engine performance circuit and take a look at it. Take note that these here terminals are located on the 13-volt auxiliary relay panel. These terminals here are located directly on the relay socket for this here fuel pump relay. So let's go over there and look at it. S3. So this is S3 connector, terminal 3. We come over here. Here's our fuel pump relay. Now we can see that we have right here S3. It comes down as a black wire and it comes across. There's a splice and back up, back to our ignition switch, and this is terminal 15. And this is again, it's like a 12 AWG wire, okay, 12 gauge. Now the other wire, which was going back over here and looking, this is S3 terminal 2. Now let's go back over here. S3 2 is right here, and it says it's a red with a black. We follow over, we have our splice, and again it says it's a red with a black. Well, if you look right over here, you can see there's a little discrepancy. No big deal, but if you want to look at it, there's our black wire, right, which was okay. But look at this wire right here that's coming into it. It's a red with a gray, okay? And that's only going to come over in the start position. So that wire says a red with a gray. We come over here, start position, and now it says it's a red with a black. So actually, it's my mistake. That's red with a gray, and this is a red with a gray. Alright, the whole point of this here, showing you these two wires, is these two control wires, they are not fused either, okay? And I already looked at these others, and they're not fused either. So the control wires are not fused if you want to look at a 110 amp fuse. Again, I can only speculate. They're using a tap rule, you know, for that. Personally, for me, if I was designing this, you know, I would have some fuses in there, you know, to protect this stuff. Now let's take a look over here to the contact side of this. Now this fuel pump relay, this relay right here is a very important relay as far as controlling a lot of circuits. It is not just for the fuel pump. And let's take a look at that. Let's follow this red wire down, goes up, and you can see that it goes to a fuse bracket. Now this fuse bracket is the one that's located out there right behind the battery. That 110 amp fuse I showed you, that 50 amp fuse right there is located right in there with all the others. So we got a 50 amp fuse, comes up, goes to the relay contact. Now, comes around, goes around, comes around, and it's going to come out on blue, terminal number 2. Alright, let's take a look at that. Let's keep following this 12 volts. Let's keep following it, see where it takes us. Now we got a blue, comes up, we have a splice. Now we got all these fuses here. So there's our fuse, 10 amp fuse, that'll protect the fuel pump. Then of course we have all of these other circuits here. Now here's what I was telling you about that fuel pump relay. That joker is controlling, sorry about not highlighting the diagrams, but we'll get through it, okay? So this one circuit that we're following right now, we're following 18, we've got a leak detection pump. We have the purge solenoid. We have the mass airflow sensor. These two splices here. We're going out to the O2 heater. Same for this one right here. O2 heater, okay? That was just that one circuit. along with the other. Now, let's follow this back out, and we can see that it's taken off and going to 19 and also to 22. So let's follow them out. 19, secondary air injection pump relay coil. 22, secondary air injection solenoid valve. And I went over some all this stuff here in the video series I did with the secondary air injection system. Okay, off of that one circuit, we've got all of that stuff. Okay, and also just a quick look. Let's see where else it takes us. We go through, going through this fuse, coming out. We're going out to a red with a violet. We're coming out over here on 2. There's a red with a violet. We're coming down here, coming down, and look at here. We are feeding all of these injectors. All of these fuel injectors is being fed for a B plus right through that fuel pump relay. So, you know, it's telling me it's got a lot of current that's coming through this here particular relay. Also, while we're thinking about that one, let's also go back to this load reduction relay. Alright, if you look at this load reduction relay, we already kind of looked at the coil side, but let's look at the contact side. There's our 110 amp fuse, goes to the contact closes. Now we're coming out on D, so let's go to 3 of 3. So here we are, 3 of 3, there is D. Now look at this bus, right, and look at all of these circuits right here. Okay, so that joker is feeding a lot of stuff. I mean, we're looking at the blowers, climatic control, the washer, heater nozzle, memory seat control module, glove box, wiper washer, relay. So a lot of stuff that tells, you know, so there's a fair amount of current. So all right, why am I telling you all this? The reason I'm telling you all this about the relays, the fuel pump relay and also for the load reduction relay, is there's a lot of current going through that. Now, these relays, 13, 14 years old. Now that's cycling off and on. That means it's going to be burning and pitting every time these contacts close. Now over a period of time, that's going to actually build up resistance across these contacts. Now just like we mentioned about the corrosion, if you have contacts that are burn or pit, then you're going to get a voltage drop across it. Anytime you get a voltage drop, automatically you're going to have heat. Now that heat is going to be dissipated, comes right out, and the wires is connected to those terminals. First place it's going to start to heat up. So here's what I'm going to do. I'm going to replace every relay that's up underneath that, up underneath there where that relay center is. Now some of the others we can get by, you know, they're not pulling as much current, but they're cheap. So go ahead and replace them. That's the way I'm going to do it. So I've already ordered the relays for $100. I can get them all replaced. No big deal. This way I don't have to worry about this and, you know, some other issue that might pop up, you know, where relay contacts get a little burned, pitted, and, you know, and then I'm getting low B plus because of the fuel pumps. And this thing, like I said, fuel pump relay, this thing is supplying all of these sensors pretty much, the mass airflow sensor and all those others we looked at. So another thing, okay, another thing, since we're talking about relays, now I've showed you this here before, okay? You've seen this, I've showed it to you. Now, when I'm working on cars and especially stuff that's inaccessible, is up underneath there, and I want to know what's in there, where's the relays at, all of these relays are not in there. So for my particular case, with a 2001 Volkswagen Jetta GLX VR6 2.8 liter manual transmission, this I took and I converted it into this. Okay, so this here is electronic copy, so anytime I want to know what's in there, then I'll know. So you guys can see that everything that's highlighted is what I actually have. I've actually put in here the purpose of it, what relay number it is, It's got on there 12 volt 40 amps, and here's the VW number. You can actually type these numbers in. You can go to Rock Auto and you can actually see these exact numbers. And I'm just gonna, you can read it just as much as I can, so I don't need to go through and show it to you. So you can sit there and look at it. This way, if you want to know which one is which, then this way you'll have this as a reference for you also. Okay, I'm going to cover one more thing, and this is for my good buddy Dave over where his channel is Spelunkered. He had a couple of questions. He would like to know more about how these solenoid windings work. One is called a pull-in winding, and the other one is called a hold-in winding. And, you know, it's the interaction of what happens. The other question was, when you start, why does the current start and go so high before the starter motor actually is turning? Okay, all right, Dave, let's just see if we can figure this thing out. All right, so we have our 12 volts. It's coming down, go through the start switch, comes around, goes to here. So we have plus 12 volts sitting right there when the ignition switch is in the start position. Again, we're going to have the 12 volts sitting up here at the top of this here clutch pedal switch. Now we press the clutch pedal. That's going to close this contact, puts 12 volts right here. Now as soon as we get 12 volts here, then it's going to apply 12 volts here. Then that means this here coil is going to be energized, the magnetic field is going to pull the relay contact over, and then here comes the 12 volts. Now we have our plus 12 volts sitting right here. Okay, so we have our 12 volts here, and we're going to move right over here, and we notice that on the battery, the positive side of the battery is connected over here, so we have plus 12 volts right there. So once we get the 12 volts applied to the solenoid terminal, then you notice that we have these two coils. Now, these two coils, one is called a hold-in. That's going to be this one right here. And this one over here is going to be called the pull-in. Now, the reason that we have two of these coils is that when we first take and put the 12 volts right here, we need a really strong magnetic field to make this here solenoid contacts close, which is going to engage. Now, here's what's going to happen. This one right here, you see how it goes straight to ground? Well, this one is going to stay on all the time. That's why it's going to be the hold-in, and we'll explain what's going to happen to this pull-in. Now, once this here solenoid two windings gets energized, and look how it's getting the ground for this one right here. You notice it's coming down and it's going through this winding. This is the field winding of the starter motor. This over here is the armature. So it's getting its ground through the field winding and the armature winding. All right, so the magnetic field comes along, pulls this here contact, pulls it over, and once it does that, then we're going to have plus 12 volts right here. But now notice, we have 12 volts on this side of this coil, and we have 12 volts on this side. So the difference in potential is 0. So therefore, this coil, you can think of it as dropping out. Okay? So it pulled in, but then it dropped out. This one over here continues to hold in, right? You know, to continue, because once the contacts change state, that means the solenoid is moved. And once it's done that, then we don't need a strong magnetic field to hold in the contacts. So we need both of them to get over the initial part of movement. But once it moves, then we only need one to actually hold it in. Okay, all right, Dave, this here, as you mentioned here, we're going to have this 12 volts up here. And then when this contact comes over, because this here solenoid windings pulled it in, then the 12 volts is going to come down, goes through the field winding, and then it's going to go through the armature winding and then to ground. Notice that this here winding, this field winding, is in series with the armature winding. Now this is what they call a series wound DC motor. Okay. Now some of the advantages of why they do this and putting the field in series with that is it gives the motor a very high starting torque. And a load here such as the motor being very constant, it's not going to vary. One of the disadvantages of having this is that this has poor speed regulation. Okay, so this motor, you want to have it always on the load, which you're always going to have the engine there, so it's going to be a constant load. If you ever take off you take one of these starter motors off, and you notice how if you don't have a load on it, this thing will just sit there and really fly. Well, that's one of the disadvantages. It doesn't have, like I said, it's got poor speed regulation. Okay, some of the things where you want to put this in is like say in a crane, maybe electric motor, because the load is always there. It's real heavy, so you need a high starting torque, and that's what these type of motors is good for, as far as the field winding being in series with the armature. Another thing is, and you won't probably find this in the starter motor, is that you will have the field, okay, is straight, and then we'll take the field winding and then we'll put it right across the armature. Then they call this a shunt wound field, where shunt means parallel, with the armature. What that one will do, it won't have as high a starting torque, but at the same time it will have very good speed regulation from like a no load to a full load, so your speed will stay pretty much constant. You remember I was telling you about how this type of motor, the series wound, has very poor speed regulation, and you could probably relate to this. If you have a cylinder or two, let's say it's totally dead, no compression. Well, one of the things they do in diagnosis is, you can crank it over, and if you hear the speed going up and down, right, then you know that your compression is not even. So what's happening there is the load is changing, and this here motor doesn't have good speed regulation, then that means it's going to be going up and down. Now, at the same time, if we had one with a shunt wound field, now even if we had, say, 1 or 2 cylinders here, so we're going to have a different load, you'll probably notice that speed will be pretty constant. Okay, so that's the difference in kind of the series wound and as an example, series wound and a shunt wound. Okay, now for the question about why do we have a high starting current and then the current will come down. Well, one of the things is a DC motor is you can think of that like a generator. Give you an example. If you can find a motor that's got the armature and it's got permanent magnets, say, for the field, okay, you go to the armature with your windings or the leads that's coming out going to the armature. If you'll go take your ohm meter, put on there, you'll measure resistance. Now, if you turn the motor and have your voltmeter, say set it for DC volts, then you will see that it will actually produce voltage. The faster you turn it, then the higher that voltage will go up. So what will happen is that when the voltage is applied to the motor, which is to the armature in the field, then we're going to have a very low resistance. I looked up the resistance. I wasn't quite sure, but I saw it said for a 12-volt ignition system on a car, starter motor, they were talking about 0.05 ohms. So when you apply the 12 volts right there to the solenoid windings, and eventually it's going to get there to the motor, then what we're going to have is you're only going to be looking at the DC resistance of the windings. So if we have that 0.05 ohms, and we got 12 volts divided by 0.05 ohms to give us current, so what is that, like 250 amps. Now, as soon as the motor starts to turn, then the motor is going to be generating a voltage. This voltage, they call it a back electromotive force. So basically, as the magnetic fields are interreacting between the armature and the field, it's going to produce a voltage on its own, and it's going to be a voltage that's in opposite polarity to the source voltage. So the net effect of the voltage that the motor is going to be seeing is the difference between the applied voltage and the back EMF. Okay, so that's going to bring the current down. So you'll have, now since we're turning this here starter motor over, then this here voltage should be pretty constant because we have a constant load. So it all comes down to is the back EMF is, like I say, is countering this source voltage. That's going to lower the voltage, which in turn, if you take that, divide by resistance, then that's going to bring the current down. And of course, as the speed slows down, the back EMF comes down, so we go back to getting more voltage, to the motor. If you want to read more about that, and you can look up Faraday's Law and also Lenz's Law, L-E-N-Z. Hope that helps you out, Dave. If you got any more questions, or maybe if I wasn't clear, just let me know. And to all of you guys, I think we beat this horse dead enough. So let's just close the video out, and I want to thank everybody out there for watching the video series, and you guys take care.